This is lesson 5.3 regarding the double angle formulas. If you take out your chapter 5 formula sheet, you'll see these formulas listed here at the bottom of your sheet. So what makes these double angle formulas, notice how we're doing the sine of 2 theta, cosine of 2 theta, and tan of 2 theta. So first off, the sine 2 theta identity is equal to 2 sine theta cosine theta. This was actually one that came up in our 5.2 homework assignment from last night because it's connected to the sum formula. So if we think about 2 theta as being theta plus theta, we could connect this back to the formula that says the sine of A plus B is equal to sine A cosine B plus cosine A sine B. So if we start to write this out, we've got sine theta cosine theta plus cosine theta sine theta. So these two are really the same, although they are in a different order, the sine and the cosine. They're just being multiplied together, and we can change the order of things when we multiply, and it stays the same. And so since they're the same, it's sort of like they're like terms, so we can put them together with a 2 in front. So it's kind of like saying x plus x is 2x, so sine theta cosine theta plus sine theta cosine theta is 2 sine theta cosine theta. So that's a little bit about the first one. Now, for the cosine 2 theta, what's interesting here is you'll see that we have 3 forms of the double angle identity. So the first option is that cosine squared, it's cosine squared minus sine squared. And the way that it connects to the other two has everything to do with the Pythagorean identity that cosine squared theta plus sine squared theta is equal to 1. So if we were to look at a variation of this, we could say that sine squared is equal to 1 minus cosine squared. So from the original statement, if cosine squared minus sine squared is equal to cosine 2 theta, let's keep the cosine squared the same. It's subtracting sine squared, so let's replace that with 1 minus cosine squared. So off to the side here we can see that sine squared is equal to 1 minus cosine squared. So if we put that in the parentheses, now let's go ahead and distribute the negative and we'll see what happens. So we have cosine squared minus 1 plus cosine squared, and altogether that's going to equal 2 cosine squared minus 1. So that's how we get the first of the variations. Now if we go back to our Pythagorean identity, we could do something similar. Instead of subtracting cosine squared from both sides, we could subtract sine squared from both sides. So cosine squared is equal to 1 minus sine squared. And if we do the same thing, we'll replace cosine squared with 1 minus sine squared, and then we're still subtracting sine squared. So we're just doing a substitution there. Altogether, that's going to be 1 minus 2 sine squared. And that's how we get the other variation. And then the double angle formula for tan is 2 tan theta on our numerator over 1 minus tan squared theta on our denominator. All right, so we're going to look at a few examples that involve these double angle formulas. So first is going to be to find the exact value of the cosine squared of 105 degrees minus sine squared of 105 degrees. Now, just first glance, looking at this, 105 degrees is not a unit circle angle, so it seems that it would be very difficult to find the exact value of this. But using our formula for the double angle of cosine, remember that cosine 2 theta was equal to cosine squared theta minus sine squared theta, and that's in exactly the same format as a problem that we've been given. So what we can notice here is that the theta that we're dealing with is 105 degrees, and so we could replace this, or we could simplify that to just be cosine of 2 times that theta value. So when we do 2 times 105 degrees is very helpful, because it's going to give us a unit circle angle. That's going to give us 210 degrees, which is really the same thing as 7 pi over 6, if you want to think about it in radians. And so the cosine value of that is negative root 3 over 2. So you'll see some of these types of problems in the assignment. Just look to match it up with one of our formulas, figure out what theta is, and it should end up being something simpler that we can actually use our unit circle for. All right, so here's another sample problem using our double angle formulas. So the information that they've given us is that the sine of some angle theta is equal to 12 over 13. Our angle theta lies in the second quadrant. So in thinking about setting up our drawing, let's go ahead and put a right triangle in the second quadrant. We know that sine is opposite over hypotenuse. We know that the third side length value is 5. But we're going to make it a -5 because in the x direction, x values are negative in the second quadrant. So we're going to need our triangle drawn and labeled to answer each component. So first, let's find sine of 2 theta. So using our double angle formula, that's equal to 2 sine theta cosine theta. And we're just going to look at our triangle to get these values. So we're going to bring the 2 down. Sine theta is opposite over hypotenuse, so it's 12/13. Cosine theta is adjacent over hypotenuse, so it's -5/13. So this just turns into a multiplication of fraction problem. Let's rewrite the 2 in front as 2 over 1. It's nice to check and see if there's any common factors you can cancel from the numerator or denominator. In this case, there are not. So we're going to multiply all the way across our numerators to get -120. Multiply across our denominators to get 169. We're not able to simplify that. Do not put it as a decimal. In fact, you will not have your calculator for this. And so we need to be able to do these using our knowledge of fraction operations. Now, really quick, a common mistake that I sometimes see on this problem that you want to avoid is that students will say that it's 2 times the sine of 12/13 times the cosine of -5/13, and then they don't know where to go from there. We're not going to say that. The sine of theta is 12/13. It doesn't turn into the sine of 12/13. We can't do that. So let's try to avoid that. It's just turning into a problem with only fractions when we make our replacement. Okay, for the double angle formula for cosine. So what's nice here is you can actually use any one of those 3 versions that were given. You're going to get the same result every time because they are equivalent. Let's just start with cosine squared minus sine squared as the original. So again, the cosine of theta is -5/13. The sine of theta is 12/13. So we'll plug those in. Now when we're squaring a fraction, we're just going to square the numerator, and then we're going to square the denominator. So we have 25 over 169 minus 144 over 169. And using what we know about subtracting fractions, we've got a common denominator already, which is nice. And so we're just going to subtract across our numerators and keep our denominator the same. So the final answer for that one would be -119 over 169. Okay, let's talk about tan. So the double angle formula for tan, we are doing 2 times tan theta divided by 1 minus tan squared of theta. So looking up at our triangle, tan is opposite over adjacent. So tan is 12 over -5. We could just make the entire fraction negative. So think of it as -12/5. Positive divided by a negative is a negative. So we'll go ahead and make our initial replacement. And then we'll start to simplify this. So on our numerator, this is 2 over 1. So when we multiply across the numerators, -24. On our denominator, 1 times 5 is still 5. So that's the whole numerator part. On our denominator, we have 1 minus 144 over 25. All right, so let's keep going. We've got a little bit more simplifying to do. Let's For this step, let's keep the numerator as negative 24 over 5. Now for our denominator, we have to change that 1 into an equivalent form of 1. We could do that as 25 over 25 to get the denominators here to be the same. And now we can subtract across our numerators. So again, we have that 25 minus 144. We had that in the previous problem. That's going to be negative 119 over 25. Now I want to show you a trick here, what we can do with our numerator to achieve the goal of getting the top and bottom denominators to be the same. Because if we can make these denominators the same, what's highlighted here, then we can just simply cancel them. And so the trick is to go ahead and multiply this top fraction by 5 over 5. So that's turning it into negative 120 over 25. Keep the bottom fraction the same. And now that we have our denominators the same, they can cancel. And we're left with negative 120 over negative 119. Negative divided by a negative is a positive. So we have 120 divided by 119. So again, you will not have your graphing calculator for this, and so you will need to be able to do all of these fraction calculations by hand. So the tips that I've shared with you here, I think, will be very helpful. All right, next we're going to see how we can verify an identity using the double angle formula. So in this identity, our goal is going to be to show that the left side is equal to 1. Let's go ahead and rewrite cosine 2 theta as cosine squared minus sine squared. When we bring down the other part, we could put together the negative sine squared plus 2 sine squared equals positive 1 sine squared. Bring down our cosine squared, and this is our Pythagorean identity. That equals 1. All right, for this last identity, let's set the left side to be our goal because that is the less complicated side. So we're going to work on the right-hand side, show that it's equal to cotangent. So we've got two double angle situations. We've got cosine 2 theta on the top, we've got sine 2 theta on the bottom. So in thinking about our goal, eventually cotangent, we know that that's going to be cosine over sine. And so we only want there to be one term on the numerator. We just want a cosine. We don't really want this 1 that's here. And so in thinking about the options for what to plug in for cosine 2 theta, I would probably think about choosing the second choice because it has a negative 1 in there, and that could cancel with that positive 1, making that go away. Now really you could plug in any one of the options and still do work with it to manipulate it to equal what you want it to do, but that might be the easiest one to plug in for the numerator. So I'm going to go ahead and make that substitution on the top. Now we know on the denominator sine 2 theta is 2 sine theta cosine theta. There's only one option for that, so that's easy. Now let's do some simplifying. So the 1, positive 1 added in front with the minus 1 at the end, those will cancel. That's going to leave us with 2 cosine squared over 2 sine cosine. And we can do some more canceling here, so our 2's can cancel, and then we can cancel 1 cosine on the top with 1 cosine on the bottom. So that's going to leave us with cosine over sine, which sure enough equals cotangent, and that's what we were trying to show that it was equal to on the other side. So those are a few examples for how we can use these double angle formulas.